So, today we're going to look at a couple things. We're going to look at composite and inverse functions. Now, this is the idea is a little abstract, but I'm going to give you kind of a real world kind of example. Let's say you have some factories, and one of them takes in, raw ore, and it outputs some kind of metal. I don't know, maybe aluminum or something. And you have a second factory, and they take in metal, and they output car parts. Doors, hoods, wheels. And then you have a third factory that takes in the car parts, and of course it produces a car. This is kind of what a composite function looks like. These are functions. They have an input, an output, domain, and a range. And this factory, this guy's range becomes his domain. He has a new range. And likewise, this factory, has this range and outputs the final result. Now the thing is, you could kind of bring all these factories together, or these functions, and look at it as, well, we put in raw material, and out pops the car. And that's what a composite function really is. Right? You're combining two functions to create one function. All right, let's take a look at an example here. Let's say you have a function f of x equals x plus 5. We know what this does. You give it a number, it gives you back that number plus 5. The domain can be all real numbers, and the range be all real numbers too. You can get any number out of it. As a second function, we have x squared. Okay? We know what this function does. You put in a number, it squares it. You put in a positive number, you get out positive. You put in a negative, you get out positive. Put in 0, you get out 0. Right? So we can form a new function, which we can write one of two ways. We can write it this way. We'll talk about what this means. But we have some notation. We use this little circle to mean the same thing. We would say this f of g of x. We could put an x here, and we would call this f of g of x. Now, what does this do? Well, let's insert what g is. That's x squared. Right? What does f do with what you give it? Forget that we're using the same letter x here. What does f do with what you give it? It adds 5. So f of x squared becomes x squared plus 5. Takes what I gave it and adds 5. So this is how you compose functions. It's a composition of f and g. Now, there's something a little different from most operations we do. If I do this different, if I switch these, g of f, which is g of f of x, what happens? Well, that's g of x plus 5. And what does g do? It takes whatever you give it and it squares it. So this is x plus 5 squared, which if we want to expand it is x squared plus, this is our a plus b squared pattern, 10x plus 25. Well, you can see these are definitely not the same, right? What we say is f and g, the composition is not generally commutative. Remember the commutative property says 2 times 3 equals 3 times 2. We have the same thing for addition. It's not true of composition, so it's a little different. Right. Does everybody have maybe a piece of paper, some scrap paper? I'd like you all just to try this. Example. If f of x is 2x plus 4, and g of x is 3x minus 1, why don't you try and find f of g of x? Why don't you work on that for a minute? All right, does anyone have an answer for this one? You want to throw out a guess? Not a guess. Informed guess.
I don't know if this is right.
That's fine.
6x plus 11.
Okay. Anyone else get that? Uh-oh. Don't worry about that. They wouldn't raise their hand anyway. But we're gonna check in a minute. But one way to check is to try a number. See, I'm looking for f of g of x. So let me pick a number. I'm just going to pick a nice simple number, 0. So 3x minus 1, well, if x is 0, and this is minus 1. So I'm going to plug in minus 1 to f. Minus 1 times 2 is minus 2 plus 4 is 2. So let's try 0 plus 12 times 6 is 0 plus 11. And you got 11. So, you know, you can check. It's not too hard. Does anyone else want to throw something up? The only person here with any guts. Everybody else is a win. No? I can't taunt you into coming up with something, can I? All right. So g of x is 3x minus 1, and I want f of 3 of x minus 1. So what does f of x do? It takes it, whatever I give it, multiplies it by 2. It's my 3x minus 1. And adds 4. Okay. So 2 times 3x is 6x minus 2 plus 4. 6x plus 2. Okay, now if I plug in 0 here, it works, right? This is kind of, this is like, like riding a bicycle, you don't really know how to do it, you fall over, and then suddenly it's like it hits you, oh, that's what we're doing here. Okay. Before we leave this, I just want to point out something so we'll see some contrast. This function, its domain is, it could be all real numbers. We didn't say, so it's all real numbers. And pretty much any number can come out of it. Any real number. We're plugging it into this function, which again, can take any real number. And what comes out of it is any real number. And this function here has that same property. Our domains and ranges, they're all real numbers. That's not always the case, and you actually have to be a little careful. When you plug in g here, its range needs to match the domain of this. Okay, what do I mean by that? Well, let's say f of x was 2x plus 4 over x. Well, there's some number here like x is 1/3, which would give me a 0, which I can't plug in here because I'd be dividing by 0. So while the domain could be anything, when I combine the two, this and this, I have to exclude 1/3. Otherwise, I'd be dividing by 0. All right, next example. This is kind of a simpler example in some ways. And g of x equals square root of x. Okay, so f, whatever I give it, I add 1. G, whatever I give it, take the square root. Now what's the maximum domain I can have for the square root? We're not talking complex or imaginary numbers, just real numbers. What numbers can I plug into this? Or what numbers am I allowed to plug in? Can I plug in 4? Can I plug in negative 16? You can? What do I get?
Like an imaginary number? It's like
Yeah,
fill
but
it
I
out.
just said no imaginary numbers.
Oh, sorry. I didn't hear that.
Oh,
My bad.
okay. If this is the domain is x is greater than or equal to 0, right? This, the domain could be anything, all real numbers. All right, so we're going to combine these. So g of x. And that's going to be, okay, f is going to take in the square root of x. Okay, so f just takes whatever you give it and adds 1. Okay. So this is still my domain, right? I have that square root of x. I can only put in positive numbers. This had as a range the same thing. This has a different range because I can, this by itself has a range of all, numbers greater than 0, but I added 1. So its range becomes numbers greater than or equal to 1. If I were to graph it, so here's 1, and the graph kind of looks like this. So the y's are just above 1. Right, well, just for the sake of argument, let's look at g of f of x. That's g of x plus 1. So g takes whatever I give it and finds its square root. Square root of x plus 1. Now the domain here is a little different, right? Here I could give it a -1, and that's all right because I just square root of 0. So its domain could be, right? But now its range, well, it's just whenever you have a square root like this, it's just going to be greater than or equal to 0. Okay, so the point here is when you combine functions this way using composition, first of all, it's not commutative. The order you do things matters, usually, not always, usually. And the domains and ranges can get more complicated. You might have to think about what the domain and range of a function is. All right. So that's composite functions. I'm going to talk next about inverse functions. But I want to remind you that the function is just, it's some kind of domain, which in my example is going to be pretty small. It's just these 3 numbers. There's a range. Think of this as the inputs and the outputs. And there's a mapping between them. So, for example, I might map these this way. I might just say 1 goes to 5, 2 goes to 6, 3 goes to 7. There might be an algebraic way of showing that. Like I could say x plus 4. Right? That would tell you how to get there. But there might not be. There might be like -8. That's a perfectly good function. Now, some functions like this are what we call one-to-one. I'm going to go back here. That is, each element in the domain has exactly one element in the range. And that's called one-to-one. But you might not have that. you might have something like this. You might have, see, 1, 2, -2, 1, 4, 4. Okay, now I could express this as x squared, right? This is a good example of something that's not 1 to 1. Why? Because both 2 and -2 both go to the same element. I shouldn't even put it there. I should just kind of draw this mapping. So why is this important? Well, we'll get to why this is important in a second. I want to draw the graphs of a couple functions here that you're probably familiar with. Say f of x equals x squared. You might know that this is a parabola. And in fact, you know, if I have number 1, that goes to 1. -1 also goes to 1. So this is not 1 to 1. Now, you may remember we had a test to see if some graph is a function. Remember the vertical line test? Right? The line goes through 2 points, it's not a function. Well, here we have the horizontal line test. It can still be a function, but if it doesn't pass the horizontal line test, meaning it goes through 2 points, then it's not 1 to 1. Should have left room here, but I didn't. We'll make room. This function, however, f of x equals x cubed, this is a 1 to 1 function. Kind of looks like this. So if I have a point here, 1 goes to 1, -1 goes to -1. Now, here's what's important about this 1 to 1-ness. Let's say, you know, I have my function, x squared, so I pick some number and I get some value. I go to 2 and I get 4. What if I wanted a function that went backwards? It takes me from 4 back to 2. Well, for this function, which is not 1 to 1, I have a problem. 2 different numbers get me back, you know, get me, did I say that right? Yeah, 2 different numbers get me back. I'm going to say that right. What's wrong with this? Here, like, 2 goes to, I'm sorry, 4 goes to 2, negative, I'm sorry, having one of those Tuesday before Thanksgiving afternoon moments. Have to think straight here before I talk. My function 2 goes to 4, or -2 goes to 4. So if I have a function that goes backwards, 4 goes to 2 and it goes to -2. Oh, that's not going to work. That's not a function. This function, on the other hand, I can go backwards. Instead of going to x cubed, I can have some function, which I'm going to write with a little -1 here, which does not mean to the -1 power. It means the inverse. If this is the cubed root, then whatever number I give it, whatever number this gave me, I can go back. And that's what we call an inverse function. It's a function that takes the range of one function and it takes it back, the numbers back where it came from. So 5 goes to 1, 6 goes to 2, and 7 goes to 3. Now, sometimes figuring out how to write the math for this is easy. Let's look at this example. F of x equals x plus 4. I want to know how to write the inverse function, the function that takes me back. So here's the process. And this is the pearl of wisdom today, how to find an inverse function. I got everybody with me? First, let's put a y here. Y equals x plus 4. Okay? This is just one way to write a function. Now, switch the x and the y's. So, first step, write it with a y. Second step, reverse the x's and the y's. Third step, solve for y. Well, if I subtract 4 from both sides here, I get minus 4. And that becomes my inverse function. Let's see how that works over with this this function here. F of x equals x cubed. All right, so y equals x cubed. I'm going to switch x and y. And now I'm going to solve for y. So y cubed equals x. I find the cube root of both sides. Y equals cube root of x. Now, these are very simple examples. You could have a more complicated example where solving for y is more difficult. But that's basically how you do it. Now, let's see why that doesn't work here, really. I say y equals x squared. Okay, so let's switch x equals y squared. And now I'm going to solve for y. So I want to find the square root of y squared, square root of x. But really, it could be positive or negative, couldn't it? So I get y equals plus or minus the square root of x. Oh, that's a problem, because that's not a function. It gives me two values. Now we can fix that problem. Again, this is probably the second most important thing today. If we restrict the domain of the first function in the right way, we can end up with a function where we can, it's a one-to-one function, and we can find the inverse. Let me show you how that works. Here, I'm going to change this function. I'm going to say the domain is now x greater than or equal to 0. Well, what that means is this whole part of the graph goes away. And now, the horizontal line test passes. And now, the minus goes away. Like magic. So if you have a function that isn't one-to-one, if you can make it 1-to-1, you can find an inverse. Remember, 1-to-1 means each member here goes to 1 here. There's only one place for it to go back to, and then you can find the inverse. All right. We're packing a lot in today. And so, you know, there'll be a little practice on the homework. But, you know, something you could bring in questions next week or, you know, the final week. There won't be anything too extreme here. If you go on to pre-calc, you're going to get this in droves, so now you have a little start. There's one more really cool thing about inverse functions. Right? It has to do with graphing. As I said, the inverse function is the square root of x here. Let me show you what that looks like on here. Actually, at this point, we can go on here. I don't know if you can see it, but this graph is a reflection of this graph. I draw kind of a line here as the mirror. This is always true of inverse functions. Now you might go, well, that's kind of cool, but why is that? Well, you think of a point here where I pick some x, we'll call it x0, and out of it we get a y. Well, if we then graph that y0, wherever that is, I guess that's going to be, say, over here somewhere, and we find out where it is on the inverse function, it's going to go to x0. In other words, the function takes us to here, and then if we go from here to the inverse function, it takes us back where we came from. That is to say, all I'm doing is switching the x's and y's. You may recall when I said, how do we find the inverse? There's a step here where I switch the x and y's. Well, switching the x and y's is just like taking this big, board piece of paper and flipping it over along the diagonal. The x-axis goes over and becomes the y-axis, and the y-axis becomes the x-axis. So that's why this works. Okay. Just wondering. Okay, this just said that was the last thing. A couple more things. I want to repeat that if we have a function f of x, the way we indicate its inverse is we use this -1 here, which again, it doesn't mean 1 over f of x, all right? That was like an exponent, it would be 1 over x. It's not that. It's just a special symbol meaning inverse. There's one other property that might help. Remember we were talking about composing functions? Well, since the inverse just undoes what the function does, if I compose f of x with f inverse, I just get back x. And it turns out this works both ways. If I first, use the inverse function on a number, and then I compose that with the function, and get x. Before we give up, let's just try that with this. Right? I say f inverse of x. Well, I decided my inverse was x minus 4. This is kind of a trivial example. My function just adds 4, so this just becomes x. So that's another way you can check that you got the right inverse. If you compose the two and you get x, you know you're there. All right, I think that's it for today. Thank you. Do have a nice holiday. Don't eat too much turkey.